This video will be about reaction mechanisms. Okay, so reaction mechanisms, what they are is like kind of looking under the hood or looking at the reality of molecule collisions and challenging some of maybe our surface assumptions about basic collision theory. So if, for example, we imagine this process that's being shown right here, okay, we have 4 HBr molecules colliding with an oxygen molecule to generate 2 waters, 2 bromine molecules, and some energy. So it's releasing energy, it's exothermic. Well, if we try to apply collision theory to this on the surface level, like it says here, what if we suggest it, and what does it suggest in terms of collision theory? We may conceptualize what's being shown there with the red dots and the blue dot. Basically, we might imagine that the 4 HBr molecules, let's call them, and the 1 oxygen molecule all have to collide at once, because that's what collision theory says. It says they have to collide. So now we have to ask ourselves, what we're really saying happens here, let's think about the reality, is that 5 molecules are going to collide at once. They're going to collide at the correct orientation, and they're going to have sufficient energy. If you imagine trying to throw up 5 balls in the air and make them collide at once, it's incredibly difficult. Even if you have billions and billions of molecules rammed into a small concentrated space, a small concentrated volume, it's really not likely for all of these criteria to be met. It's not bloody likely, mate. So how does this reaction actually happen? Well, how it happens is through a series of small steps, the sum of which we call a reaction mechanism. Okay, so here's the exact same reaction. I'm going to prove to you that it's the exact same reaction, but drawn out into a series of small steps, or we could think of them like little smaller collisions, more reasonable collisions to propose, or even small subreactions. The whole thing is called a reaction mechanism, okay? So here's the reaction mechanism to make that previous reaction shown. So all of this, you could also look, this is called the reaction mechanism here, okay? All these steps combined. So there's kind of 4 steps, there's 3 steps, and then the last one's repeated twice. What we can do is we can look at this like we kind of look at a math problem. We can say, if we total up, if we kind of sum up everything on the right side of the yield sign, and we sum up everything on the left side of the yield sign, we can cancel out redundant species, and then they won't appear in the overall reaction. So let's have a look at what we've got. We've got one of these like HOOBr things there, and we've got one there, so let's cancel it. We have 2 of these HOBRs there, and we have 2 of them there, so let's cancel them. Everything else looks like it is where it belongs. So we have 1, 2, 3, 4 of the HBRs, and we have 1 oxygen there. And then, and again, there's the oxygen. Here's the HBRs. Okay, and then on the right-hand side, we've got 2 of the bromines, Br2, and we have 2 of the waters, H2O. There we go. So as you can see, if you go flip back, if you rewind the video and go back and look, this is our target overall reaction. So that's called the overall, okay? So when you cancel out the redundant species, you get the overall reaction here. Now, if you look at some of the species involved in the various steps of the mechanism, you can see, because we are able to cancel them out, that they're part of the mechanism, but they're not a part of the overall reaction. And some of these have important roles, and we can identify them. So I'm going to highlight in yellow what we call reaction intermediates. So one of them is this HOOBr species, and another one is this HOBr species. And there's 1 of them on the right and 2 of them on the left, like this, okay? So these are what we call reaction intermediates. Reaction intermediates. Okay, they are produced in one step, and then they're consumed in a subsequent step. not necessarily the very next step, but they're consumed in either the next step or a step somewhere thereafter. Okay, and so these reaction intermediates can form little like temporary species that exist, but they don't exist in the overall. And so that's the other thing there. They are not found in the overall equation. Not found in the overall equation. You can also have catalysts turn up in the mechanism, and we'll show in a minute how those catalysts turn up in the mechanism. What you'll also notice here is that I've not addressed this yet, but you can see that when we look at the rates, or I've made a little comment on the rates of each respective step, and one of those is labeled slow, and the other ones are labeled fast. And that's really all we care about with the mechanism, generally speaking, is which one's the slowest step. And that is because the slowest step in a mechanism is often referred to as the RDS, the rate determining step. Okay, and what this means is that this slowest step of all the steps in the mechanism is going to control the rate of the entire process. So the rate determining step controls the rate of the whole process, and I'll show you why. Alright, so we can show this with our favorite kind of diagram, the potential energy diagram. So this is how you might imagine the potential energy diagram looking for the whole mechanism. And if you're wondering, like, what are we looking at here? Well, remember in the first step we had it produce this little Huber thing here, HOOBR, then the next one it produced like HOBR, and then this last one happened twice, but it got us to the actual products. Or, eventually got us there. And this one was the reactants, the initial reactants. So we can imagine it's kind of split up into these three processes. Well, if you look at the height of the humps, okay, you look at the height of what is ultimately representing the activation energies, of course, whatever hump is going to be the highest, it's not always the first one, but whatever hump is the highest here, we're comparing that one to this one to this one, okay, this is the biggest activation energy here that had to be overcome in the whole thing. So therefore this is going to be the slowest step. This is going to be the rate determining step, as we call it, okay? And the rate, these are other ones, are then going to be faster, and that's going to be faster than the slow one, okay? And the idea here is that the whole rate of the reaction is controlled by the rate determining step. It's kind of like a bottleneck. You can think of the RDS as kind of like a bottleneck. Imagine you're driving somewhere and there's an accident on the road. Okay, it's like you're only going to get to your destination as fast as you can get by that accident on the road. Okay, it's literally, if you think of a bottleneck, fluids only pour out of a vessel based on the width of that bottleneck, right? So it's like a bottleneck. The whole reaction is going to happen as quickly as that slowest step allows, or as that highest activation energy step allows. Okay, so the only thing we haven't shown on this exemplar mechanism is what would a catalyst look like if it were in there. Okay, so we'll show that in an example in a second, a catalyst, how that comes into play. And also, a lot of students ask me, like, well, how am I supposed to know these mechanisms? How would I know what these, like, little baby steps are? Or how would I know which one's the fastest or slowest? You have to be given, you could never come up with these out of the blue, generally. You could propose them and guess them, but, like, you'd just be guessing. You have to be given them, or you have to be given some set of partial criteria that allows you to fill them in, or you have to be given a lot of information to make the whole story here. It's not like you have to come up with these out of the blue. Okay, so have a look at this example. Pause the video and see if you can answer all these questions. Okay, hopefully you took a crack at it. If you didn't, well, here we go. given the following mechanism, and there's step 1, 2, 3, they tell you which is slow, they tell you what's fast, and they show you all the species involved. Write the overall reaction. So to make the overall reaction, remember we're just going to like kind of write everything on the left side and everything on the right side, and we're going to cancel out all the redundant stuff. So let's cancel out everything that's redundant. We see an H minus on the right and H minus on the left. We see a OH minus on the left and an OH minus on the right. We see a HOO minus there and an HOO minus there. Does anything else cancel? I don't think so. So overall, it's CO, carbon monoxide, plus oxygen, plus nitrogen monoxide, turning into carbon dioxide and NO2. This looks like something that might happen in sort of like a catalytic converter of a vehicle. Well, maybe not, because it still produces NO2. Kind of nasty. But anyways, that would be the overall reaction. And then we need to identify any reaction intermediates. Okay, so let's, I'm just going to kind of code these with the blue highlighter. All right, so reaction intermediates, remember, are things that first show up on the right-hand side, like H minus here, okay, and then they are used up in a subsequent reaction by on the left-hand side, by appearing on the left-hand side. So H minus is one of them, and I'll just highlight like that. Another one is HOO minus, because there it appears for the first time, and there we use it up. And I think that's it for those. A catalyst. Okay, it's the first time we've seen a catalyst. So a catalyst kind of acts like, well, it appears sort of like an intermediate, but in a little bit different way, almost the opposite way. A catalyst does not appear in the overall reaction. Maybe I can give you a little, maybe I can write this to the side here. So it does not appear, it's not in the overall. And instead of first appearing on the right-hand side, it first appears on the left-hand side as a reactant, and then it gets canceled. So it's not in the overall, and it appears first as a reactant, and then, of course, it gets canceled. Reactant, it gets canceled. So you may have already identified what that is. In this case, it is the hydroxide, OH minus. Okay, so it's there at the start, see? It's not in the overall, and there it is once again produced at the end. So we include it in there, and it's regenerated at the end, unchanged and unconsumed, and that's what makes it a catalyst. Okay, and then finally, what's the activated complex for step 3? Oh, blast from the past. Remember these activated complexes? So remember what that means is the reactants for step 3 kind of all combine together. So if you knew the actual bonding, you could, kind of show the complex bonding here. It's a bit much in this case. I think you can represent it simply just as like a HOO, NO, and then don't forget that the whole thing would have a negative charge. Or you could just write NO3H with a negative charge, and that would be fine. By the way, in this one, I might just add one more little tidbit, which is I did include the fast, slow, fast for the different steps there. So if you were to consider that, which one of those steps would have the lowest activation energy? And you should recognize that this means the middle step, step 2, would have the lowest activation energy of the 3. All right, here's another example. Again, pause the video and take a crack at answering these ones. So first off, can we determine step 3? A little bit of a different question this time. How do we figure out what should be in step 3 of the mechanism? Well, you look at what's in the overall. All we want remaining on the left-hand side in the reactants is this kind of NH2NO2. So that's right there. So we want to make sure this stays there, but we have to make sure the other two cancel. So we've got this guy canceling. That's fine. But we certainly have to make sure that this guy, I'm going to circle him in blue, we have to make sure that this one cancels out somehow. Okay, so let's make sure we get one of those on the right-hand side, CH3COO minus. Okay? So that kind of takes care of what we would expect to have on the left side. On the right side, we also see another thing that we need to make sure we cancel because it doesn't appear in the overall. So all we should have in the overall, I'll circle those in red. We should have the N2O, and we need an H2O. There is no H2O, so we have to add an H2O. Let's put an H2O here. That better get produced because we need it down there. And we need to get rid of this CH3COOH. Okay, so let's make sure we put that on the left. CH3COOH. And then there's got to be one more component here, and of course, it's this guy here, right? The hydroxyl OH. We have to put that there as well, and we see it doesn't appear in the overall. So therefore, finally, we would cancel those hydroxides, and we would cancel these. I guess what are they? They're ethanoic acid, something like that. Acetic acid, it's like the vinegar acid. And we would cancel this as well. Okay? So we'd be left with what we're meant to be left with. Right? Hopefully you can see that. Then if we're identifying reaction intermediates, let's do it the same way we did before. We'll kind of highlight them in, I don't know what color we used last time. We'll highlight them in blue. I think that's what we did. Okay, reaction intermediates are going to be in blue. They're produced in one step and consumed in a subsequent step, and they don't appear in the overall. So, looks like this guy's going to be one of them, right? Right. And it looks like hydroxide ion is going to be another one, right? First shows up on the right-hand side, used over there, cancel. And, we have another one. This NHNO2 is going to be another one. Okay, so we have 3 reaction intermediates here. And then for the catalyst, highlighting it in green, it's going to be this acetate ion, CH3COO-. It first appears on the left-hand side, and then in a subsequent step of the mechanism, it is regenerated unchanged. And so I think we've accounted for everything. The only thing left is the activated complex for step 1. So the activated complex for step 1 means we want to jam all those atoms together that are reacting in step 1. So we could either just draw this big, ugly NO2, put them all in there, CH3COO, and don't forget the whole thing has a charge. Or we could maybe clean that up a wee bit and kind of try and combine different atoms. So what do we got? We got 2 N's, and we have 2 C's, and we have, 4 oxygens and a slew of hydrogens, something like this. So you could draw either one of those, and that would be a fair representation of the activated complex. How about the rate of the thing? I don't know, they didn't give us any data about what's slow or fast, but this is how we manage and understand and conceptualize what reaction mechanisms mean and some of the major players in reaction mechanisms.